A colonist stands in the red dust, boots planted, holding a compass the way explorers have held one for 1,000 years. The needle spins, not settling, not calming, just spinning erratically for several seconds too long. Then it stops, not pointing north, not pointing anywhere related to the planet at all. It locks downward and slightly forward, aimed at an ordinary-looking rock a few meters away, a rock indistinguishable from 1,000 others nearby, except that this one is quietly magnetic and right now stronger than the entire rest of the planet combined. Your compass on Mars won't point north. It will point at whatever rock is closest. That is not a malfunction. That is the correct reading. A compass works on Earth because the planet has a working engine underneath it. A molten, churning iron core generates a global magnetic field. Scientists call this a dynamo effect, the same basic mechanism as a power plant turbine, just built from liquid metal instead of coiled wire. That dynamo produces a consistent north and south magnetic pole, the same 2 points anyone, anywhere on the surface can navigate by. It is stable. It is planet-wide. It does not care where you are standing. Mars does not have that engine anymore. Roughly 4 billion years ago, Mars's core cooled. The churning stopped, the dynamo shut down, and the planet's global magnetic field collapsed entirely, leaving Mars with no organizing structure for compass needles to align to. That single number is worth sitting with. 4 billion years is not a recent event, and not a partial one. It covers almost the entire history of the planet. Every dust storm, every ancient riverbed, nearly all of Mars's current climate and radiation exposure trace back to that one collapse. But the field did not vanish without a trace. While it was still active, pockets of the crust became magnetized, particularly ancient volcanic rock. It locked in the direction of the field at the exact moment it solidified. A field can die and still leave fingerprints. Scientists call this crustal remnant magnetism. It is scattered unevenly across the surface, patch by patch, with no relationship to any global north or south. Some patches are far stronger than others. A compass on Mars is not responding to a planetary field because none exists to respond to. It is responding to whichever local magnetized rock happens to be strongest and closest. That could point in any direction at all, depending entirely on where you happen to be standing. The compass is only doing what the physics allows it to do. The instinct every colonist would carry from Earth is simple. Every rocky planet with an iron core should generate a magnetic field, the same way it works at home. Maybe weaker, maybe stronger, but structurally the same. Pack a compass as a lightweight, batteryless backup. No moving parts to fail, no battery to die. A tool that has survived every century of Earth exploration precisely because it needs nothing but a needle and a magnet. On Mars, that same logic collapses the moment the needle starts spinning. That logic works fine on Earth, it fails completely here. If Mars's field were simply weaker, this would be a minor inconvenience. A weak but still consistent field would still point somewhere reliable. You could calibrate for a fainter signal the same way you adjust for a dim flashlight. Turn up the sensitivity, filter the noise, and the direction still comes through, just fainter. That is not what Mars offers. There is no consistent direction to calibrate against because the magnetism is not organized around poles at all. It is scattered in isolated patches, some many times stronger than others. Intensities and orientations can flip entirely across a distance of just a few kilometers. Weaker would have been survivable. Absent is not. Think of a radio searching for the strongest signal in a city with no central broadcast tower, only scattered pirate transmitters of wildly different power, hidden in different neighborhoods, each one broadcasting on its own, none of them coordinated with any of the others. The radio will lock on to whichever transmitter is loudest and closest. It will give you a clear signal, strong and unambiguous, exactly the kind of confident reading you would trust on Earth. But that signal tells you nothing about where north lies for the city as a whole. It only tells you which nearby pirate transmitter happened to be shouting the loudest at that particular street corner. Move 3 blocks over and an entirely different pirate station takes over, just as confidently, just as wrongly oriented to anything citywide. The city has no tower, only locals shouting. Move to the Terra Sirenum region, and the compass problem sharpens into something dramatic. This stretch of the southern highlands holds some of the most magnetized crust ever measured on any rocky planet, up to 10 times stronger than comparable crustal magnetism found anywhere on Earth. That is not a faint trace buried in scientific instruments. It is strong enough to visibly deflect a compass needle from meters away. The kind of magnetic pull that would make a hiker's compass swing hard and lock, no subtlety involved. Strong here does not mean reliable anywhere else. A compass near one of these anomalies would not drift gently. It would swing violently, locking hard onto the local rock with a force strong enough to overwhelm any faint hope of a planetary signal. Walk 10 kilometers away to a patch with weaker local magnetism, and the needle's behavior flips again, drifting, refusing to settle, wandering without any obvious pattern at all. 10 kilometers is not a long walk. It is an afternoon's hike, and yet it is enough distance to turn a confidently wrong compass into an aimlessly wrong one. There is no recalibration that fixes this. A compass needs one thing above all else: a stable, planet-scale directional signal. Mars simply does not have one to offer, no matter how the instrument is tuned. The obvious fix to anyone hearing this for the first time sounds like an engineering problem. Build a more sensitive compass, filter out the local noise electronically, use better shielding to block interference from nearby rock. Surely, with the right calibration, the signal could be separated from the noise the same way engineers isolate any weak reading buried under interference. None of that works, and the reason is worth sitting with. A noisy signal can be filtered. A weak signal can be amplified. But this is not noise layered over a real signal, and it is not weakness that better engineering could overcome. There is no planetary field underneath the noise to recover. The problem is not signal quality. The problem is signal absence. No amount of instrument refinement produces a direction that does not exist in the underlying physics of the planet. You cannot filter your way to a signal that was never being transmitted in the first place. The needle is loud. It is also lost. Picture a metal detector sweeping a field with no buried treasure at all, only a few old magnets scattered from a demolished machine, left behind by accident, half buried and forgotten. The detector beeps. It points, confidently, exactly the way it is designed to. It has found something real. It just has not found direction or treasure or anything worth navigating by. It has found scrap, mistaken for a signal, and no better detector would change what is actually buried there. A confident answer is not the same as a correct one. Or picture a lost traveler surrounded by a crowd, everyone shouting a different direction, each one completely confident, each one speaking only from their own local vantage point, none of them able to see beyond the block they're standing on. There is no one voice carrying city-wide authority, no elevated position from which the true direction could be seen. You get an answer. It is loud, immediate, and confident. It is simply whoever happened to be standing closest and shouting hardest. That is what a Martian compass hears every single time. Never silence, never a clear planetary voice, only the nearest local shout. In 1997, NASA's Mars Global Surveyor entered orbit around the planet, carrying a magnetometer, an instrument built to measure exactly this kind of magnetic signal. The mission scientists, led by principal investigator Mario Acuna, had a reasonable expectation walking in. They anticipated one of two outcomes: a working global field, weaker than Earth's but still organized, or a dead, uniformly quiet planet with no meaningful magnetism left at all. The two outcomes anyone would have predicted from Earth-based intuition, the two outcomes that would have made sense. Neither happened. The instrument instead detected strong, localized magnetic signatures concentrated in the ancient southern highlands crust, not a global field, not silence, a patchwork, intense in some places, absent just kilometers away, arranged in no discernible planetary pattern at all. It was not the answer anyone on the team had drafted a paper around in advance. A magnetometer found a ghost, not a field. That discovery was the first direct evidence that Mars once had a global magnetic dynamo of its own, one that had since shut down, leaving behind exactly the frozen, fragmented crustal magnetism now confusing compasses on the surface. A single orbital instrument had reconstructed from magnetic fossils alone a piece of a planet's ancient internal history, decades before anyone would stand on the surface holding a compass to confirm it firsthand. The rock a modern compass locks onto is a direct descendant of that discovery, a tiny local echo of the same ancient signal Acuña's team first identified from orbit, a signal now shrunk to a scale that fits in one gloved hand. Since 2014, NASA's Maven orbiter has been mapping this crustal magnetism in far greater detail, cataloging where the strongest and weakest anomalies sit across the entire Martian surface, patch by patch, region by region. Humanity now holds a nearly complete picture of exactly where these unpredictable magnetic patches are located, essential information for any future mission that might otherwise rely on magnetic instruments without knowing where the anomalies would strike. The strongest anomalies concentrate in the oldest terrain on the planet, the same southern highlands geologists most want to study for clues about Mars's ancient, wetter past, the very ground most likely to hold answers about whether the planet was ever truly habitable. The regions most interesting to science are, by the same underlying cause, the regions where a compass behaves worst. That is not a coincidence. Both facts trace back to the same ancient rock, magnetized at the same ancient moment before the field that created it ever disappeared. Old terrain and unreliable compasses share the same cause. The rock the compass locks onto is not a landmark. It is not a resource. It offers no clue about water, no clue about minerals, nothing a colonist could actually use for survival or navigation. Its only distinguishing feature is that it's solidified at a particular moment billions of years ago. A magnetic field that no longer exists happened to be pointing straight through it at that exact instant. The compass is not broken. It is not lying. It is functioning exactly as designed, faithfully reporting the strongest magnetic signal within range. It is simply reporting a fossil, not a direction. A fossil rock and a dead atmosphere turn out to be relatives. The failure runs deeper than a broken gadget, though. The same collapse of Mars's global magnetic field that ruined compass navigation also removed something far more consequential: Mars's shield against the solar wind. On Earth, the magnetic field deflects the constant stream of charged particles pouring off the sun. It protects the atmosphere from being slowly stripped away, particle by particle over geologic time. Mars, once that shield fell, had no such protection left at all. The shield fell. Everything downstream of that followed. Over billions of years, the solar wind gradually stripped Mars's atmosphere into space. It thinned from something plausibly wetter and denser into the cold, dry, near-vacuum world it is today. This is not a minor side detail attached to the compass story. It is arguably the single most important consequence of the entire magnetic collapse, more significant to Mars's history than any localized anomaly could ever be. The same ancient event responsible for a spinning compass needle is the leading explanation for something far larger: why an entire planet transformed from a world that may once have supported liquid water into the desert it has become. A silly navigation failure and one of the biggest open questions in planetary science trace back to the exact same moment in deep time, 4 billion years ago, when a planet's core simply stopped churning. A dead atmosphere and a dead compass share one ancestor. None of this means Mars is innavigable. Every real mission architecture already plans around the missing field. Engineers stopped assuming magnetic navigation the moment Acuña's data came back in the late 1990s. Inertial guidance systems track motion directly without needing any external signal at all. They measure acceleration and rotation internally, building a position estimate from motion alone. The same principle used inside submarines that spend months without any outside reference point. Radio triangulation from orbiters and the GPS-like satellite constellations proposed for future Mars infrastructure provide position without ever touching magnetism. The same timing-based principles that let a phone on Earth locate itself from satellites overhead. On the surface, rovers and future colonists lean on sun position tracking, gyroscopic instruments, and terrain features cross-referenced against orbital imagery, methods that Perseverance and Curiosity already use daily without ever consulting a magnetic reading. None of those systems care whether the ground beneath them is magnetized. None of them ask the crust for a direction it cannot reliably give. The broader lesson sits underneath the specific failure. Any navigation technology built on assumptions specific to Earth's particular geophysics has to be re-examined from first principles the moment it is carried somewhere else. Obviously, it should work the same way is an instinct, not a law of physics. Mars is not the only place that instinct fails. Mercury shows similar patterns of crustal magnetism, frozen fragments of a field that no longer functions the way it once did, discovered by later missions using the same kind of orbital magnetometer that first caught Mars's anomalies. Any planet or moon whose internal dynamo has permanently shut down will leave behind the same kind of patchy, fossilized signal in its rock, waiting for whoever eventually lands there with a compass in hand. No engine runs forever. Planetary magnetism is not a permanent feature bolted onto every rocky world. It is the temporary product of a very specific internal condition, a molten, actively churning metallic core running for as long as the heat inside a planet allows it to keep moving. That condition can start, it can run for billions of years, and it can simply stop, the way Mars's did. What remains is a frozen, fragmented record embedded directly in the stone. Not erased, just permanently paused, the way a photograph outlives the moment it captured. The needle on that Martian compass is not confused. It is reading exactly what is there. An old, ordinary-looking rock, magnetized in a moment that ended long before anyone was around to see it happen, still faithfully pointing at whatever remains of a planet's oldest and quietest secret.